Topic explores machine learning and prediction techniques used to improve forecasting accuracy and decision-making in finance. The topic emphasizes that predictive modeling has become increasingly important because financial institutions must analyze large and complex datasets in rapidly changing market environments. Machine learning methods complement traditional statistical approaches by identifying nonlinear relationships, handling high-dimensional data, and improving classification performance. The program explains that predictive models are widely applied in credit scoring, fraud detection, trading strategies, customer analytics, and risk forecasting. Effective prediction models allow financial institutions to allocate capital more efficiently, detect emerging risks earlier, and enhance strategic planning within competitive financial markets. A major topic within the topic is logistic regression, which is commonly used for classification problems involving binary outcomes. Unlike ordinary linear regression, logistic regression estimates probabilities bounded between 0 and 1, making it suitable for predicting events such as loan defaults, fraud occurrences, or credit rating changes. The program explains that logistic regression transforms explanatory variables through a logistic function to estimate event probabilities. Analysts evaluate model effectiveness using classification metrics such as confusion matrices, sensitivity, specificity, and prediction accuracy. In finance, logistic regression remains highly valuable because it provides interpretable probability estimates while maintaining computational efficiency and statistical rigor for practical predictive modeling applications. The topic also discusses categorical variable encoding techniques, which convert non-numeric information into formats suitable for machine learning models. Financial datasets frequently contain categorical variables such as industry classifications, geographic regions, or customer types. The program explains that these variables must be transformed into numerical representations before being incorporated into predictive models. Common encoding methods include dummy variables and one-hot encoding. Proper handling of categorical variables is important because poor encoding choices may distort relationships or create misleading predictions. Effective variable representation improves model performance and allows analysts to incorporate broader information into quantitative forecasting frameworks used in portfolio management and enterprise risk analysis. Another important concept covered in the topic is regularization, a technique used to reduce overfitting and improve model generalization. Overfitting occurs when a model captures random noise in historical data rather than meaningful underlying relationships, causing poor predictive performance on new data. The program compares ridge regression and lasso regularization methods. Ridge regression penalizes large coefficient values while retaining all explanatory variables, whereas lasso can shrink some coefficients to zero, effectively performing variable selection. In financial applications, regularization is particularly valuable because datasets often contain many correlated variables. These techniques improve model stability, interpretability, and forecasting accuracy in complex quantitative financial environments. The program further introduces decision trees and ensemble learning methods. Decision trees classify observations by repeatedly splitting data according to explanatory variables that maximize predictive separation. The resulting tree structure is intuitive and easy to interpret. However, single decision trees may be unstable or overly sensitive to data variations. Ensemble methods address this weakness by combining multiple models to improve predictive accuracy and robustness. Techniques such as random forests and boosting aggregate predictions from numerous learners to reduce variance and bias. In finance, ensemble methods are widely used in credit risk modeling, fraud detection, and market forecasting because they often outperform individual models in predictive performance. The topic also examines k-nearest neighbors, KNN, support vector machines, SVM, and neural networks as advanced classification techniques. KNN predicts outcomes based on the characteristics of nearby observations within the dataset, while SVM identifies decision boundaries that maximize separation between classes. Neural networks consist of interconnected layers of nodes capable of learning highly complex nonlinear relationships. The program highlights that neural networks have become especially important in modern finance due to their flexibility and predictive power. Applications include algorithmic trading, image recognition, fraud detection, and sentiment analysis. However, advanced machine learning models may sacrifice interpretability and require substantial computational resources and careful model validation. Overall, topic demonstrates how machine learning techniques enhance predictive modeling and support more sophisticated financial decision-making processes. The program emphasizes that successful predictive modeling requires careful data preparation, appropriate model selection, regularization, and performance evaluation. Logistic regression, decision trees, ensemble methods, support vector machines, and neural networks each offer unique strengths depending on the nature of the prediction problem and available data. At the same time, The topic highlights the importance of balancing predictive accuracy with interpretability and model robustness. By understanding machine learning and prediction techniques, candidates gain advanced analytical skills necessary for managing financial risks and extracting insights from increasingly complex datasets.